about that. Okay. So we'll start now. Okay. So I'm not going to give many talks to you. I'm going to give one talk. The purpose of this talk is to give a general introduction about just little bit. Just in 1 hour, I can't cover too much, but I want to mainly to see what we are expecting in this conference. So just to motivate some applications kind of thing, not very specific applications, how the general kind of thing, how homogenization is got motivated, and then few things about it, and kind of various methods developed which we are going to study here for the next 2 weeks. So this is an introductory talk about the next 2 weeks, who is doing what, etc. Somewhat, not every details. Okay, that's why it's a multi-scale problems. And here there are no references or anything giving that on the way when they teach that particular topic, you can get the references. Of course, she has a book on homogenization book, and that's probably one of the first book you can follow. I don't know, there is a copy here. Do you have a copy with you?
No.
I don't think. That's okay. I don't know if the library has one. That's not here, right? So there is a copy with him. Okay, so you can have a look at that copy. Of course, I have one there in the office, but you can bring it and you can have a look at that copy. But then there are quite a few reference books and things like that, starting from our fundamental book of Ben Susan Leon's Papanicolo, where I have started studying that. That time her book was not there. And then there are books by Jikko, Kozlov and things like that. So there are books due to Dalmaso on gamma convergence. So there are quite a few books, but more on the literature, there are a lot of papers. It's quite a big area now. So I will not be going that way. So I want to see some models, basically some pictures in the beginning. Okay, so I just want to know what you mean by homogenization. Yeah, you want to see the homogenization? Maybe I'll start from here. Yeah, that's better. So I will tell what is physically what you are looking in homogenization, what is mathematically looking in homogenization. Okay. All right. So this is a picture of what is called a composite material. Most of you would have heard about a composite material. If you are using a pure material, that pure material may not have the property you are looking at it. For example, the big example which I normally tell my students, suppose you want to use a pure gold, say kind of 24 karat gold. You know that using that pure gold, you cannot make any ornaments, you cannot, it's not really useful, pure gold, because it's brittle, it will break, it will thing. You cannot make it a wire or something like that. But then if you take the pure gold and add some silver or copper into that and do a fine mixing of it, but that is what we call it a composite. One important distinction in this composite, when you are making this composite, this is not a chemical composite. Okay, the gold and copper are not interacting chemically and creating a new material. Okay, the copper and gold, it is there, whatever amount of copper, gold you are taking, whatever amount of copper you are taking, when you melt it and mix it, both are there as it is. The difference is that where this copper occupies in a uniform way or non-uniform way, depending on that, the composite, that material will have an entirely different property. Copper may have some property, gold may have, say for example, you want to understand the thermal conductivity of the material. Copper may have some thermal conductivity, gold may have some other conductivity. When you mix it, depending on the way you are mixing it, depending on the that we call it that, so you are going to hear this word microstructure. This we call it a microstructure, and depending on how this copper going and sitting there, the property, what we call it an effective property, the effective property changes. Okay, so the homogenization is all about determining this effective property. From the properties of whatever properties, so the problem comes from everywhere, not necessarily, it can be from chemistry as well. Okay, you are only chemist, right? So I should address you once in a while. So it can come from, so depending on, it can be an electrical conductivity, it can be a thermal conductivity, it can be an elastic, it can be elastic properties, it can be anything depending on what you are. So why do we make composite? Because we want to have material or of the desired properties which we look for. For example, suppose you want to make a body of an aeroplane. Generally, you have a concept that if the materials are want to have a strong body, if you use pure materials, it will be very heavy. So naturally, you cannot make a heavy metal to use the body of the aeroplane or anything. So what our desire is that we want strong material, but we want lightweight. See, this is something contradicting. Pure materials do not get this. If you use pure thing, you cannot get light. So that goes with that, the pure materials may have its own property. So you may have to design a material which is lightweight but strong. This can achieve only through composites. Okay, which is what? So this is a typical schematic diagram. So you have red and yellow are two different materials. Okay, so the total amount of yellow material is the one ratio. So that is called the ratio of this material. So this may have some ratio and red will have that ratio. Suppose you can also, you need not have to preserve. So assume that you preserve it. And instead of putting this material in this way, you make this material, so there is a periodically distributed this material. In normal things, there may not be periodicity. So periodicity we are taking for our convenience. So all the time the material may not have periodicity to understand, and that is what most of the time in this workshop you are going to have this periodic structure preserved. But in general there may not be a periodic structure. So let me tell you, then the things are more complicated to learn it. So you are, instead of distributing it in an epsilon equal to one period cell, the same amount of total yellow material is distributed in so many places. So the total amount of yellow is the same as here. It's not changing. You see, you have a different distribution of the material. This is a microstructure. And when you make epsilon become smaller and smaller, so you see when epsilon equal to 1/4, when epsilon is there, the material is changing. When you do it, end of it, you look like a material, you don't see these two material. That's what exactly your gold ornament. You have a pure gold, you mix it with copper. When you look at the gold ornament, you don't see there to mixture of two. You don't see it is copper. You don't see copper anyway. So you see it looks like a one new material. And that's the composite. It's not really view. So if you take a, so this looks like a homogeneous material. When epsilon becomes smaller and smaller, and this try to get homogenized. This is, and you are, this may have a, so if you are, even though you are started with two different materials, it will have two different properties, elasticity property or electrical conductivity or any other property. This may have an entirely different property. That's what I'm trying to say. So the homogenization is want to obtain this property of this material when epsilon becomes smaller and smaller. And what? Yeah, epsilon becomes 0 because I added 2 zeros, looks like, right? So it's not epsilon equal to, see, this fraction goes to 0. So epsilon goes to 0. It's something like epsilon equal to 1/n goes to, so infinity is not, yeah, it's epsilon is 0. Of course, this may not be realizable, right? This is a kind of realizable thing, sir. This is not the realizable thing. This is actually the realizable thing. But epsilon becomes smaller and smaller, it tends to this one. Why do we do this thing? That's what the physical property, I'll tell you now thing. So you can see some actual media. This is what the mathematical modeling of the general thing. So you see the plywoods. Plywood is a kind of arrangement. If you look at this individual materials are not really good. It is not useful. But you arrange it in an individual, that's why you make all the ornaments, all these furnitures here are plywood. Plywood is a reasonably strong material to make ornament thing. But if you look at its component material, you cannot make things. You also seen that one. Suppose you have a wood which has fibers in one direction. If you have the material, there are fibers like tamarind tree, etc. It has fibers only on one direction. So if you have fibers only in one direction in a wood, that wood cannot be used for any furniture, because you can break it in the fiber direction, you can break it easily. Perpendicular to the fiber direction, you cannot break it. So if you take a fiber in one direction, a thin slice of fiber in one direction, you take another thin layer of fiber in one direction and put it in the perpendicular way, that is a kind of, and you do it at a very small scale, then it becomes, you cannot break it in either direction. Because one direction, if you are trying to break it, the other one will oppose it, and you get a new composite, you see. So it's the same material you used by using the fiber directions differently, and you get a new, that's what effectively working for plywood. And that, there are a lot of other things like concrete. Concrete, if you take individual components of the material in a concrete, you cannot use it. But then when you mix it at the right ratio, you get a very strong, in that case you may have your elasticity equation and other kinds of equations may come. That's what you have a pillar when you are taking, just with the concrete, that pillar won't be strong. But if you reinforce it with your iron rods, immediately that will become strong. You see the material property, you cannot use just iron pillar rods also. If you put it in a reinforcement in your concrete, the pillar, and that gets strengthened. So you may have again a property of that. These are all examples of concrete. You would have seen all this anyway. And I will tell you how this is a picture from some book maybe is written. Okay, this is these are all microscopic view, okay? It's not the eye view. You have to take a piece of it and you view it through a microscope. You look at here. See, normally when you have a material, the normal material, when you pull it, pull it in a lengthwise direction, the breadthwise, the length of the breadth decreases normally, right? Here is a microstructure. When you pull it, this breadth increases. That's how when you create a microstructure in a different way, you can see that one. Pull it, this also increases. This is a kind of contradicting properties. So you can create a microstructure in which way you will have property which is not common to your common. Do you see that from this microscope? Do you see this from the microstructure? When you pull this, these are the voids. There is no material here. This is the material part. Suppose I pull this. Pull this means what? This point and this points, the distance increases, right? When you pull it, between these 2 points increases. When you 2 point increases, the distance between these 2 points also increases. So at the micro level, when you pull it, all the pulling happens, this distance also gets increased. So you can create microstructures with contradicting property. Another thing, what will happen in a normal thing, suppose you have an iron material, when you heat it, what will happen? It will expand. But you can create a microstructure, when you heat it, it will decrease the dimension. This is a kind of, this is again a material part. You see, you create a material like this. When you have a iron rod in a linear iron rod, the length increases. But when physics tells you that when you have a bent rod with a bend, when it heats up, the bending increases. That physics law, when you know that, you know that. If you have a bend, it bend increases. And if I create a material like this, you see what will happen to, look at one structure, these are all microstructure. If I heat this portion, what will happen? The distance between these two will increase because bending goes up. Similarly, the distance between these two decreases, the distance between two, so all these 4 points distance decreases, it means that it shrinks. So the iron thing, you can make a microstructure for which the material shrinks. What I'm saying is that in homogeneous, you can create materials which keeps on changing with contradiction property. That's why you can create material with lightweight and thing. And there are very interesting applications. I don't want to discuss too much, we don't have time. So you can, these are called 2-rank materials. I showed some other pictures. This is a microstructure, and the microstructure is kept in opposite direction. So These are called two-rank materials, etc. These are all some optimal materials. So you will see when you pick up, you will see when do you get the maximum, when do you get the best material, when do you get the worst material. So all you are looking at it. So I'm giving, this is other type of composites. And this composite you would have seen it. Okay. And this is interesting thing, there are different cores of material. When you, materials are, suppose you push some rays in this direction and you are watching here. You are watching, but you don't see the bending. It's something like hiding inside. And what is hidden inside, you won't get it if you watch it. You can put, do you see? These are all, it's very interesting about the conductivity, about that. You should read this. There's a very interesting book in the, what is that big book on composites? Milton's composite. You look into this picture. So it comes, it bends, then it comes and again bends back. So you are sending here, it's not really end of it, you are not getting some. So if there are some material, you are not able to recognize from here. So the outcome way is not recognizing you are already met and discussed something. So you are asking somebody to come on the way, he meets somebody and he discusses and plot, but he comes out as if he doesn't know anything, right? And you see that way. These are all various types you can show, elliptical orbit. So these are mixture of two material. Depending on where the amount of material is the same, so its property is same, total property of that material is the same. Depending on the various arrangement, the effective conductivity will change it. These are all again some optimal bounds of some of the important papers of Tartar and other things. So they, all these kind of things were studied in physics, chemistry, biology, all the areas they have this kind of estimates, but a good mathematical theory came up a little later. Yeah, these are, so if you put it in a different elliptical orbits, its property will change it. This, you know, this is the honeycomb. So the nature itself, the honeycomb, they can store it properly, honey. So the nature itself, the honey know about homogenization. Okay, the honeybees, I'm telling. Okay, so this is one type of homogenization problem which you are going to see, and various methods to handle this type of composite material. So the majority of our time will spend on understanding this kind of composites and the PDE problem associated with it. It's hot?
It's cold for us. Can we adjust the temperature?
You can, somebody can go and tell him, Abu, one of you. You feeling cold?
Of course, I too, me too, but I have a jacket.
Then come and give talk, you feel hot. Right? Yeah, okay, yeah, I know that is cold. Even after talking, I feel it. Yeah, so, yeah, it's okay, he will adjust. So this is one type of homogenization problem of the composite material, and then there will be a problem posed on such material, and then you will see the description. Okay. Another type of homogenization problem, which we may not discuss much, but I think Patricia said she will do maybe an hour lecture on perforated domain. Yeah, so another type of homogenization problems are the problems from porous media, which has a plenty of applications. For example, the oil flow underground. Oil doesn't flow like a pipe. The oil flows underground where there are many solid particles. In between there are voids. So the oil is moving underground with solid particles. These are called porous media. That is a medium with a lot of either lot of porosity or a medium. There are many solid thing plus where the fluid can flow. And this happening at the micro scale. Okay, small scale. So a typical mathematical model, we need always a mathematical model, right? You have a domain omega in which, for mathematicians, you start with a domain omega, from that you remove the holes. Okay, now it is not a composite material. It is a porous media, and these inside parts are porosity. There is no material here. So this is either, so the portion is here, this is our domain part. So same amount, of porosity. So the total volume of the porosity, you can keep it fixed or you can keep it small. Depending on that, it's very, very interesting results are there which produce. I don't know how much she will do, but maybe 1 hour or something she may do. 1 hour, right? 1 hour to give you 1.5 hour, one lecture, a little bit, but there are very interesting results depending on the total volume of the porosity remains constant or total volume of the porosity goes to 0 faster. Accordingly, your law will change. So that is why the physicists and other people understood that one. So they don't use Navier-Stokes equations to handle the fluid flow through the porous media. They use what is called a Darcy law. So physically they understood. But mathematically, homogenization way, we can establish Darcy law is the limit of your Navier-Stokes equation according to the porosity. So mathematically, you become more and more holes, the total amount of holes you see. So you will have a domain omega, removing a large number of small holes, either keeping the total volume of the holes same or total volume of the holes much, much smaller. Accordingly, you can, so you have a domain, so problem in a domain with a large, varying domain with a large number of holes, and you want to study the limiting behavior of that. That's the second class of thing. So third class, let me tell you, that's initially I was basically working in domains with perforated domains, my earlier work. But then in the 10 years back or so, we started a new area so all these students are working in this area. So let me tell you, domains with oscillating boundary. I think Professor Antonio will talk about all that things. So he will give a series of lectures on domain with oscillating boundary. And I'm just giving you some example. Have you seen this picture? Anytime? Anywhere? The modern, that's a problem with the, have you seen that thing? No, nobody has seen this. Okay, I will give you another picture. Have you seen this picture? You should tell me. This is heat radiator, right? Oh, it's sorry. The name came. Okay, name also. Sorry. This is because when you work this mechanical system, it produces heat, and you want to efficiently radiate the heat generated. So, and as you know, the physics tells you that the heat radiation is proportional to the surface area, and you cannot create a big material inside a computer, right? To keep a material so that your heat generated by. So within the space provided, within the material provided, you don't want to increase the material weight. So you have given an amount of material to create something. Within that material, you want to create a shape in such a way that the total surface area increases. So the heat radiation takes place. And this is what you do it. You see, this is one YouTuber said heat radiator. So you have below there, I didn't draw it properly, but then there will be a big domain below. On that you have small slabs. And so increase the width of decrease the width of the slabs and increase the number of the slabs. Keep it the slab. So that with the same amount, without changing the space, you can increase the number of the area of the surface area can increase. It should be effective. So what you are having is that you are having a domain. In that domain, you are having boundary. And that boundary becoming more and more oscillating. So you have a domain, again a varying domain, but not the domain with holes, but a domain whose boundary, this is keeping at the boundary with a large number of things. So the domain is something like that.
So now that they are applying for the solar cells and what?
Yeah, certain. So for us, we are working on this type of problems, and our Antonio is the kind of expert in that area. So we are all learned from looking at his papers in the beginning. Okay, we have started with all this in the beginning. So we started this whole work of thing with Ravi, and they are all doing. And we are initially when we started, we didn't even understood, but then we now understood. Thought we are understanding better. But when we start understanding better, there are more complicated problems coming. So there are plenty of problems arising automatically. When each time we stop of doing that one, then something. Yeah, each time we are in the illusion, we will stop the work because something new coming. But then you see suddenly will something new come. So that is the kind of thing. So you will see some set of lectures 3 or 4 from the master himself about this subject. Yes, these are all engines. So you do it. There are plenty of problems we can model. Our aim, we started with this figure. So you see there is a jet engine in which there are a lot of oscillating small boundary, and when you rotate it, it will rotate faster. It's possible that there will be a turbulence happening. So you can study very interesting controllability problems and control problem. Of course, we didn't reach that time-dependent control problem first, but we are doing that. Yeah, so this is the typical modeling of that. So 2-dimensional modeling with a lot of oscillation. In 3 dimensions, it may look like that. Okay, and then we are you can see. You see when the oscillations becomes, if you put it more and more, the number of the total volume is same, but the number increases. Hence the boundary. All these are more complicated because if you study boundary value problem, the number of boundaries are increasing. Even in a perforated domain, all holes, the number of dealing with boundaries in a PDE is a difficult task. And when the number of boundaries are increasing, you have to deal with a number of. And all this cannot easily handled by numerics. That is why the homogenization. Okay. So you see the picture goes like that. And looks like that you have a full domain. Do you get an equation in the full domain? What do you get averaged out? You will see all that, some of them, some of the results you will see here. This is then, with that you can have the domain with all. These are the some of our results are coming up to very nicely, which we have done. And then you see that kind of first heat radiators, if you, a schematic diagram, if you do, not only you have boundary, you have branched structure and more general domains. And there are work related to where oscillations are small, results may be difficult. When the amplitudes are big, the results are more difficult. Okay, to do that one. Yeah, so what is physical homogenization? It's a study of macroscopic or bulk behavior of solutions to partial differential equations. So you may have a differential equation posed on a domain which is a composite, and due to the variation in the property, that variation will be reflected in the differential equation through its coefficients. That's what I can. So when you model a heat conductivity problem on a domain, the heat conductivity problem will have a PDE, corresponding PDE will have a differential equation in which there will be coefficients. The coefficients essentially represents the property of the material. And if your property of the material keep on changing by due to mixing, the coefficients also changes with respect to that parameter thing. So basically you will have a PDE with a coefficient which is varying. Since the coefficient is varying, its solution will vary, and we want to understand the variation of that solution. So that's all about homogenization, if you want to give in a nutshell. So the heterogeneities can be in the form of the fine mixing of 2 or 4 material with the different physical properties in the domain, or due to singularities in the domain in the form of pores, granules, etc. The study of properties can be anything. It can be structural properties, can be electromagnetic property, can be thermal property of the composites. It can be study of fluid flow, like flow of oil, water through surface, pollution of groundwater, flow of resins and polymers in molds. All this leads to analysis of vibrations of thin structures. That's a kind of eigenvalue problem. It's like an Eiffel Tower if you want. If you look at the structure, that's a typical homogenization problem. You have a huge structure of Eiffel Tower, but you see the material, if you compare, so when I say epsilon is small, it is small compared to the place you are studying. For example, in a big building, the thickness of the wall, you may say that it may be a 2 feet or 1 feet. It is big, no. For us, it looks like big, but compared to a 20-30 floor structure, The thickness of the material, thickness of the wall is a small parameter compared to the scale of the domain. That's what exactly Eiffel Tower. You look at the tower, you will see the thickness is very small compared to the whole structure. So the smallness is corresponding to the problem. Smallness is not absolute, okay, that epsilon smallness. And you want to know whether is that. And then of course homogenization with also, there are plenty, some of them I showed here. Okay, the problem posed on the health, so we are not trying to study the existence uniqueness, you may come across, so assume that is what she will do little bit, how to study the variational formulation, its existence solutions. Okay, this is the most important thing. Due to the variations of the change in properties, the solution will also develop oscillations. So because the properties changing within a small scale, hence the solution may also change within a small scale. And that is given through the solution of your differential equation. It is not directly given. Your change in the property is given directly, but your solution is coming from the PDE. So how the solution changes, we know that solution is changes happening, but how much it will oscillate is implicitly there in the differential equation. So you want to understand that. So the understanding that is essentially homogenization. So a direct numerical study will not be able to capture either the bulk behavior because the scale of the material can be seen. When you do a numerical scheme, however powerful it is, your machines have a limitation in the discretization. So there will be a discretizing variable h. Okay, but the small scale present here may be much smaller than your discretization scale. So when you have a scale in a variation happening in your problem, which is smaller than your possible bus computer, then you cannot get any good results doing that numerical thing. So to handle this numerical scheme, first you have to do some sort of homogenization, then apply your numerical scheme where there is no epsilon parameter. Yeah, so this is what, suppose you take a sine wave. When you get this is sine 2x, sine 10x, 5x or sine 20x, so you see sine x becomes oscillating more and more. This is what you will see, so your coefficients are oscillating more and more because in a small scale it is doing. Okay, you are going to anyway listen this next 2 weeks again and again. So basically we do the problem again and again with various methods. Okay, so you may get to know what, it will take some time if you are doing it for the first time, if you are listening it for the first time, but over a period of 2 weeks, we expect you to get some good feeling about homogenization. So you see, and when you have an oscillation, how do you, so suppose you want to compute numerically sine 100x, it's not possible. Or 1000x, it may become more and more oscillatory, and which you don't know how to oscillate it, how to get numerically that's it. And this is there through the differential equation. So you have to solve your differential equation, which you may not be able to do it directly. So that is what we are expecting an asymptotic analysis. That is, we try to approximate the solution corresponding to the heterogeneous medium by the solution of a homogeneous problem in which the small parameter does not appear. So if you recall my composite media, for each epsilon you will have a PDE. Different epsilons you will have a PDE. Then epsilon tends to 0, you see a kind of heterogeneous, homogeneous media, you want to get a PDE corresponding to that. So basically what you are looking now, let me come to the mathematical form of it. Basically, you have a family of differential equation. You want to understand the limiting behavior of that family of differential equation. Okay. So the mathematical problem is to identify the homogenized equation, to prove the convergence of u epsilon corresponding to the heterogeneous equation to that of homogeneous equation, to capture those. I told you the solution, there will be an implicit oscillations. You want to capture because it's not directly given. Your coefficient may be oscillations, you are understood, but the solution coming through your PDE, and that may not have that. You want to understand. These are called characters. I don't know Anybody is doing character here? Because first you have to understand homogenization first, and character is a little more serious issue. I don't know. Ravi wants to do some character? Yes, that is why I asked you. Young people can take more time. Okay, but anyway, learn it. First homogenization properly. The solution together with the characters can be used and also can be computed numerically to get good approximation to the original problem. So you have an epsilon problem, find the limit problem, use the limit problem, solve it numerically. That may be a good approximator to an epsilon problem when epsilon is small. Okay? So let me write down a little mathematics. You have to begin with. And next 2 weeks you are going to live with this equation. Okay? So keep that equation. This is one of the most simplest elliptic equation. But don't get carried away that only this type of equations can be handled. Once you learn it, but this is fundamental to do anything. Even if you want to do parabolic or hyperbolic or other type of PDE, the first objective is to understand this. This is a second order equation. All of you are familiar with this equation? I hope so, right? Please let us know if you are not following something. Not today. Today, this is a kind of overall lecture. After that, in between, you don't understand, please let us know. Okay? We want it to be like an interactive discussion meeting. That's why we named it discussion meeting. Neither a workshop, nor a school, nor a conference. Okay, so this is exactly a discussion meeting where we want discussion to take place among you and ask. Please do not have any inhibition. Don't think that how do I ask such a silly question. In your mind, you may think that it is a silly question. You don't have to worry about. The moment we have a doubt in our mind, you don't have to think that it is silly. Okay, you are thinking others will think, others don't think, others also had that same doubt either, or they would have had that kind of doubt earlier. So don't worry about any silly issues. Please ask and clear it and once and for all. Okay, so this is a second order equation, and this is what oscillations are taking place. See, epsilon becomes smaller, and suppose Aij is equal to sin x. Then Aij of x over epsilon will be sin x over epsilon. And epsilon becomes smaller and smaller. This is getting oscillations faster and faster. This will lead to oscillations here. Okay, so that is what doing it. Yeah, this is what I said, rapid oscillation. So what is the homogeneous equation? Some fundamental difficulties with you. Why are we doing this workshop? What's the problem in handling such problems? So let me, I have another, okay, 10-20, I have 20 minutes. To do that one, some fundamental difficulties, mathematical difficulties. Okay, engineers will construct without all that. Because the composite material they constructed many decades back. Homogenization came up starting from 70s. So they can't wait for homogenization. They understood physically what will happen. They started doing it. So suppose this is, sometimes you may have difficulty, but look at this coefficient. What are the information given to you? Just think that it's a mixture of two material. In that case, Aij takes only two values. Suppose two material having conductivity alpha and beta. So Aij takes alpha or beta as exchanger. The problem is that because of the microstructure, exchanges are very small, the alpha and beta getting changed faster and faster. When epsilon becomes smaller and smaller, when the mixing is finer and finer, the material changes. The occupying the material place changes. The moment exchanges a very little, immediately it will jump from alpha material to beta material. Again, within a small change, it will change it to beta material to alpha material. So it's a keep on changing that one. And this you cannot capture easily numerically. And that oscillations, but whatever it is changing, but it is changing between alpha and beta. That means your Aij has some sort of a bound. Aij is changing, but the bound is not changing. So Aij is basically bounded by alpha and beta, if it is a mixture of two material. These properties, mathematicians, beautiful way classified as ellipticity basically. So to have more general thing, this is the basic one thing behind the ellipticity notion. Because this is, so if you have a matrix, you are looking for this property in a more sophisticated way, you call it elliptic, is essentially is the positive definiteness of this matrix. Okay, the age is basically telling that it is positive definite, and the component in the matrix do have a nice bound. It will not go to infinity, nor the matrix, its determinant or anything will not go to 0. So you have an ellipticity on the left side. That means you have a bound from the left side and you have a bound on that from the right side for the matrix A. A is equal to Aij matrix. Whenever there is a bound for a matrix, you know that from finite dimensional thing, whenever something is bounded in finite dimensional situation, that will have a convergent subsequence. Or if you are working in some space, it will call it, that is where your functional analysis will come. So I hope if you are not comfortable with the functional analysis, this is the, so the PDE is nothing but functional analysis. So you have to have a very strong background in functional analysis. If you have problem of that kind of weak topology, strong topology, please let us know, so that we can help you in the evenings and other times in giving some informal lectures about functional analysis, whatever we want it. So whenever you have a family of functions which is bounded in some space like L2 or something, then that will not produce a strong convergent subsequent, it will produce a weakly convergent subsequent. So you should know what is a weak topology, etc. So that is where the problem in infinite dimension. So this is an issue of infinite dimensional spaces, because we are no longer working in finite dimensional spaces. You are working in spaces like L2 and more Sobolev spaces. Some of them are mentioned in that book, or anything which you are trying to distribute. So with that comments, you can always say that whenever you have an oscillatory function, that oscillatory function, so for example sin x over epsilon will not converge point-wise. Sin x over epsilon, no point-wise convergence. You have to understand that one. He cannot getting oscillator, but then you know that f epsilon fx will converge weakly the sin x over always in L2 space, any L2 interval. Okay. More generally, if you take any periodic function and oscillate it, that function will always converge weakly to its average. The sign has an average 0 in a full period. So this is the first theorem you have to learn in homogenization. And that's the first few pages of her book, I suppose, if I remember. Every periodic function, any book you homogenization, any periodic function oscillated, that oscillatory function will converge weakly to its average. So this converges to its average. But then your PDE analysis comes, not homogenization. And using the PDE analysis, which she may do something like, these are the Sobolev spaces where you are looking for solutions. On this Sobolev space, you can also derive U epsilon converges to U weakly. So you have a Aij epsilon converges to weakly, U epsilon converges to U weakly. So our tendency, if you look at this converges, this also U epsilon converges to weakly means grade U epsilon converges to weakly in L2 space. U epsilon converges weakly in H1 space, which is the Sobolev space, is same as telling us U epsilon. The implication is that the corresponding U epsilon will converge, grade U epsilon will converge to grade U in thing. So that's what we are telling. Okay. U epsilon converges weakly to U in H1 naught. This is a Sobolev space. If you are not understood, you will learn soon. Or if you are not learned in her lecture, learn it by tomorrow morning. So evenings you can learn. Ask somebody. Here almost 90% people know it. Those who are not learned, please quickly learn it. This will imply your grade U epsilon will converge to grade U in L2. L2 is set of our square integrable function. You know that. Okay. So this converges weakly, but weakly is a very weak thing. It's a dangerous thing. Weak convergence is one of the dangerous guy. But that's all the information available to us. That's the problem. You don't have a strong convergence, you have only weak convergence. Weak convergence has no respect for anybody. Okay, it will not obey the rules of the strong convergence. For example, if you have two if you have two sequences, say Cn converges to C, Dn converges to D, then you can immediately say that C and Dn converges to CD. But if it is in the function space, and if you have two sequences U epsilon and V epsilon, U epsilon converges weakly to U, V epsilon converges to weakly to U, then U epsilon, V epsilon may not converges to UV, but still possible that U epsilon, V epsilon may converge to something. But then how do you recognize that something? And that's the whole, so if you want to put everything, whole PDE in just one line of what is PDE and a research, I say that PDE research is overcoming this. How do you get the product of two weakly, understanding the product of two weakly convergent subsets? If you can do that, you can do many of the problems without much difficulty. So, your immediate thought will be this will converge weakly, this will converge weakly. You may think that immediately you can write your limit equation, this one. That's our tendency. If that is true, if the product of Aij converges to Aij epsilon converges to M of Aij, U epsilon converges to weakly, grade U epsilon converges to grade U, you may think that this into this will converges to this into this. That's a natural expectation for majority of people. If that is true, you have an equation for U and you have a homogenization is done, all our jobs are over. We have nothing more to do in that case. Unfortunately, we are in a happy situation. This is not true, right? Suppose if this is true, basically we are all will be jobless because we don't have any job there. Okay, because the whole problem, all the problems are done. You may. Yeah, they used, but it was wrong. But engineers understood immediately. They have done some sort of meso-averaging. They didn't do that. Okay, they understood this is wrong. Okay, but then you don't know. But then what is your equation? You have these are the two information available, nothing else. You want to use this equation to get your limiting PDE. Okay, so that's it. That's where and in one dimension you can see you don't need to have a homogenization. See, within one dimension, these are all n dimension what I mentioned. One dimension, if you do it little more cleverly, you don't need any technique from homogenization. Due to the one dimensional nature, I'm sure Editha may be presenting that one dimensional problem. You can see that one dimensional problem you can see, and your limit is this one. You see, so then we expected the limit to be this one, right? Minus d by dx of ma into du by dx. This is what? But ma is replaced by ma m of a minus of minus. That means you invert a first, a epsilon first, take the limit and then again invert. So these things are not a commutative operations, okay? So that is why I say you take the average of 1 over a, not the average of a. That is nothing but the limit of 1 over a epsilon, not the limit of a epsilon. So you invert your a epsilon, take its limit, again you take its inversion. So an inversion, limit and inversion. So the inversion and limit is not commutative. If it is commutative, it would have been easy to get cancelled and you would have got this answer. Both are same. So even in one dimension, which you can work out easily without any technique, okay, and you get this equation. So this is where your issue. You can easily see that this goes to 0, but if you take the product, it goes to half. Okay, so you have an issue. So what is so another 5 to 10 minutes, we quickly finish it. So let me put it very mathematically now. Forget about all your, mathematical community who do not know any. So you, depending on that, if someone asks you homogenization, first understand what is he. If he is coming from a mathematics, not community from applied maths or understand PDE, don't start with whatever I said so far. Okay, so if you are going to give a lecture, you start with this thing, and they will be pleased. Okay, so to please them and then tell the other facts. So to take a reverse order. So you have a space in which you are considering all types of matrices which is symmetric and satisfies one. So you are assuming this matrix of functions, the entries are functions. Symmetric means Aij is equal to Bij, and it satisfies this thing. This is typically the bound which I say if it's alpha and beta property. And this property is called what is called the ellipticity. This is called the L infinity boundedness. Okay, so then only you call it a post-elliptic problem. There are issues. If this is not satisfied, your differential equation, it is a degenerate elliptic equation. In the degeneracy of the sign changes, and you may have an issue of existence. You may not get a unique solution and all that. You need some sort of uniqueness and all that. Okay, you may have problem if you don't have ellipticity. And so you choose a matrix like that, corresponding to that you have a differential operator and you have a corresponding differential equation. This is our situation. So any matrix here, matrix function, you have a differential equation. Now what are you trying to do it? You are trying to take a family of differential operator, right? Because this is changing according to epsilon. That means you are looking for a family of matrices here. Corresponding to each family of matrices, you will have a family of differential equation. So because your coefficients are Aij of x over epsilon, that means you are looking for a family. And then you are looking for the convergence of that one. So what are we looking at it? Corresponding to that one, you will have a family, you are looking for a family, and you want to know a convergence in such a way that the solution should satisfy that one. End of it, you want to get a PDE, right? You want to get so you will have a family of PDE. You understood that family, just replacing Aj of epsilon by its average will not work. The AM, I'm talking about not the theorem now. I'm looking for an AM. So given a family of differential equation, I want to identify my differential equation, limit differential equation, which is also given by an element here. In other words, given a family, I want to identify some limit. I don't know the point-wise limit or the average limit which I said do not work. That's a problem. So I do not know it will have a limit or not. But if I say that there is a limit like that, so that the corresponding PDE converges to the PDE, then I say that convergence is H convergence, which definitely Patricia will introduce soon. Okay, so the H convergence is something like that. The solution should converge. This is essentially the PDE will converge. Okay, you see, this is average converges, this separate average, but the product is converging to some other product. It is not the product given by the average. If that happens, then I say that this corresponding family of matrices converges to a matrix which we call it H convergence. H may be homogenization, D for maybe the D George, or it's a Green's function. So there are how this name came up, whatever it is. This is what you are going to do it. So the whole 2 weeks, you will see various methods to analyze this. Okay? So you have and there is a compactness theorem, which you will see together. So let me skip all that, which you will see. So in a nutshell, one has a family of differential operators, and we would like to obtain the limit operator. In some sense, the limit behavior of differential operators. And that's what we are going to do it. And you will see that. The differential, let me make a remark. Though we started with the differential elliptic operator, it need not be elliptic. It can come from any other situation. But studying for elliptic operators is more or less more fundamental even in other applications. So in this workshop, I don't think you will see other than elliptic operator. So in the beginning, you will essentially see only elliptic operators. So you don't have to worry. So let's start with what is in this discussion meeting you are expected to do it. Any asymptotic problem is there. The first method people try is asymptotic expansion. The problem is that how do you identify a good asymptotic expansion? If your asymptotic expansion, because asymptotic expansion is not a rigorous method, it is a kind of formal method. Okay, there is no rigorousness in that. So if you choose an asymptotic expansion which is not good, you may lead to wrong answers. Maybe she will show something, if at all. Otherwise, you will pick up. So you have to have a correct asymptotic expansion in that problem. So she will discuss about the asymptotic expansion. Then the first methods initially after this asymptotic expansion, there are methods like using test functions, compensated compactness. I hope Patricia will do some of the things about method of test functions, Tartar's method of test function, various names. I don't know what she preferred to call, but it's almost, oh, there is a time, very good. But I started 3 minutes late. Okay, so let me come. Then there is a two-scale convergence introduced in that 1989, if I am right. Yes, or 1990. Ravi Prakash will talk about that one. And there are something, block wave analysis of the 1990. Block wave is an old subject of physics, but then it's also a Fourier method by Nandakumaran. And method of unfolding is a very recent method, 2000, and we plenty of it use it. Okay, and Daniel will give a set of lectures on that. And then there was an old method. This gamma convergence method was introduced in the 70s, not for homogenization problem. It was a variation convergence introduced by D. Giorgi and other people. But then that also can, I will not do an elaborate thing because we don't have time to everything. These are all more important. This, I may give just 2 lectures on gamma convergence, but then Harsha from IIT will give just 1 lecture on the application of gamma convergence to homogenization. So just 3 lectures will be covered. Everyone is more or less giving 3 lectures each on that. And then some other later topic of H measures, which I didn't have time to tell you what it is, but then anyway you will listen from the master who will be doing that. And then the homogenization with oscillating boundary will given by this has some specific interesting problems which all of our interest. All of us are interested in this. So naturally our students will get interested, or they will be forced to get interested. What else to do it, right? And they will do that one. And then Patricia will also give 1 lecture on perforated domain. Okay. And then it's a new faculty last year joined in IIT Kharagpur. He gave 2 lectures on some. This is more of probably based on his research. None of them is based on your research, our research. But then you will also next week you will see some research level talks. Okay. You will also have some problem solving and training sessions in the evening. Probably, as I said, in the coffee time or something after that we can discuss how to form some groups. So you get mixed with that. Don't get in the same group where Philippines should not be in the same Philippines group. Let's separate and mix, everybody mix. So give your style of learning in your back in your country to other group. So that would be nice that you get mixed by being in the different groups. Okay, there are 3 from Philippines, 3 from France. So you maybe will make 3 or 4 groups. So be in the groups. Some experienced people will be there. Some experienced teacher will be in charge of the group kind of thing. So we'll go that hierarchy and do some evening training sessions. And then we will have a presentation by participants last day. So those who wants to give some talk, a short duration, by the end of the week let me know. And it should be related to homogenization. So accordingly, how many I receive? The time is fixed. I want to finish by Friday as early as possible. Depending on that, it may be only few of you are coming forward. Get more time. If you are coming, more people are coming, we will have little time for 10 minutes, 15 minutes. So you just present, or you can have a presentation from the group. Okay, so we make 4 groups. Each group you present related to that work. Anything related to homogenization. That's it. Thank you for the talk. This is nothing related to that. This is our book. It's a kind of, I should do the advertisement all the time, right? So this is our book on ODE. Okay. And this is written exactly for your master's students or anyone. We prefer this to be the class test. And our PDE book is coming to, not exactly to compete Patricia. So, okay, the PDE book may come next time. That is more, what do you say? This has more advanced things like variation formulation and things like that. That is a proposal for our second book on PDE. The first book on PDE may come in more of method of characteristics. So no competition, we go together. Okay, so then next talk, she will give a brief about the, there is also a video course. So if you want to learn this, you don't need teachers. You take this book, take the video course, this is freely available, download it, study according to your convenience back home. Okay, all right. Thank you very much.